All right, lecture 2. Why build an emulator for MongoDB? I think I may have hit on some of these things, but MongoDB does basic concurrency control, and it has a limited query language. Between those two things, there's some reasons why you might not want to use it, but the reality is that there are a lot of applications being built out there using MongoDB. And all of these different applications have some sort of chunk in them that's dealing with these deficiencies. Those chunks tend to be error-prone because dealing with the deficiencies is hard. They tend to be complex, and code-wise, when you go out and look at code doing this, these pieces out here tend to be somewhere between 30 to 50% of the application code. So there's a huge batch of code out there. Now, if we'd like to be able to deal with at least the concurrency piece of it, that piece that deals with concurrency, and just take that piece out and throw it away and forget it, what we need to do is we need to go to a different database. So instead of going up here to a MongoDB that doesn't have this, go to an emulator that does. And a good way to build this emulator is if we build it on top of some database that already has all these concurrency things in it. My choice for this is Postgres. The reason for that is because of two things. The first one is it has GIN indexes, reverse key indexes, and the second one is that it supports natively these days JSON data. Now, you go, why is it important to have those two things? MongoDB is a document store, and what it stores is basically JSON data. It talks in terms of a binary version of that we call BISON data, or binary JSON data, but it's still JSON data. So having a database that natively understands and allows us to query and manipulate JSON data is a critical piece. Postgres implementation of JSON data has everything in it we need. The second thing is that Mongo creates automatically indexes for working with this data to get performance. And we're going to have to emulate that index creation, and we can index the JSON data in Postgres with these reverse key GIN indexes. So we're going to have to understand how those indexes work and why we should create them and use them. And those GIN indexes, okay, provide us a good way of getting fast access to the data, of quickly retrieving what we're looking for out of the JSON data. Now, there are some good things about MongoDB. It fairly simply implements replication. It claims to have high durability, but there are things that we can do with Postgres that get us those same features, and do it at a scale that MongoDB can't touch. Specifically, there is a version of Postgres called Cockroach that distributes Postgres across multiple machines, including multiple data centers, and will get us more durability than Mongo can ever touch, and it's already built and tested and working. So we have a path going forward for getting the nice feature of MongoDB. Now, by going to Postgres as the underlying system, we also happen to have this other feature of Postgres, which I think is useful, and as time goes on, other people are beginning to appreciate that useful feature. Tables and a schema. Because once you get done with building on this side, you may find that these applications, as they change, suddenly they may need other features, and instead of just having a document store, you can actually start using some of the other features of Postgres as well. So there's a long-term perspective of why this may be a good path to go down. Now there's lots of things that I don't know about this path, and we're going to talk about the unknowns too, and what you deal with the unknowns. But that's kind of the nice things about it. I want to talk a little bit about database history, and why in database history this is not the first time that this sort of thing has happened or been seen, and how database history affects this. In 1992, Microsoft released Access. Access is a database implementation tool. It was based on some products that they had purchased, but they significantly rewrote them. So whether or not Microsoft built Access or they purchased it is an interesting question, but underneath Access it has a SQL capability from this thing called the JET engine. And JET stands for Joint Engine Technology, allows you to access these .mdb files as your database, or it allows you to go out to a bunch of other databases like Xbase and access their files and retrieve and update data. And Access has the nice advantage of it's got a beautiful user interface, it's easy to use, you can sit there and somebody that doesn't know a lot about databases can build some sort of an application. So people started building applications. Now, one of those things that they really wanted in Access is transactions. And transactions are the way to prevent multiple people from updating the same data at the same time and give you serializability. Now, this is not full ACID compliance, but just basic transactions. Now, all of the file data is stored in files. And if you have multiple people accessing this, the way that you can lock it is by locking the file, so that each JET engine only gets to update one at a time in the data in the database. And they wanted to put this across a network so that this was on one box, but this application over here could access it across their network, and this application could access it across the network. So basically, each person was running a copy of the JET engine, but they could lock these files and get transactions to work. So in Microsoft's indubitable wisdom, they added to their ability of doing network access locks, basically exclusive locks. Now, all of these machines out here are running on Microsoft Windows, and I don't know what you think of Windows, but I think it's somewhat unreliable. And each one of these little PCs is talking across a network at the same time to the same database on some box. In any case, what you see happen in most small offices is that, I'm talking about small offices here like 200 computers, is that sooner or later somebody installs something and one of these computers goes poof and crashes. Now, if that computer that crashed happened to be holding a lock to that MDB file when it crashed, that lock is not released. In fact, the only way that we have to this day to release the lock on this file is to go over here and reboot this system. And that's a bad thing. Not a little bit bad, really bad. So, although Access has some nice features, it's got this nasty concurrency model in it. And Microsoft's solution to this is about 15 years ago, they finally did a version of Access that can use a real database instead of the JET engine, and you can use SQL Server. And when they went to that, that actually solved the problem of all of this network goo stuff underneath, because there are all these applications out here, lots of them. And there's an entire industry out here in taking Access applications and converting it to running on a real database. Now, when you do this upscaling, there's lots of what Microsoft's favorite thing involved, money. And they charge you a bunch for this. And you can look at it as the world's ultimate bait and switch. Get people to build something. Have a defect. Fix the defect with lots of money. But it does work. But there's still this industry out here of all these people dealing with access and the jet engine and the problems that the jet engine introduces. So this has been going on for a long time. You look at it and you say, well, what's the real fundamental problem? The fundamental problem is that the jet engine didn't have ACID compliance. Okay? It didn't have good concurrency controls. And it didn't allow multiple people to access it. And as we've moved into a world where instead of it being just, a few people in an office, we're distributing things across the web, and maybe we've got remote workers halfway around the world, and the reliability of the network is probably less when we put it out across the web than it is locally, suddenly this lack of ACID compliance gets even worse. So along comes the web, and we want to have databases that instead of working at this kind of a scale, now work at the scale of tens of thousands of users concurrently. And people start going, well, we can't do it with a SQL database because it doesn't have enough throughput. That's probably not actually true. But that's their thinking, and we get this NoSQL. Databases. The most common of those is two databases. One doesn't strike me as much of a database, although it is useful as all get out, and that's Redis. Redis is described as the original author as an in-memory data structure, as in it has lists and sets and hash tables and all sorts of things. It's a data structure. It's not really a database per se. And the other one that has shaken out of all of this is MongoDB. And there's a lot of applications built with MongoDB. We're probably going to discuss some of the modeling problems in MongoDB and why some of that is really crazy stuff that goes on in MongoDB. But MongoDB is the most popular. So that's the one we're going to look at. And what I see in MongoDB is the new Access. There are people out there building things in MongoDB, building all this stuff, having to deal with concurrency problems in the application, having to deal with the lack of a query language, the fact that you can't query data and sum it and roll it up, having to build reports out of it that have to walk across thousands or millions of records, millions of documents in this case, and not having any tools other than out in the application to do it. So they're patching around all of the problems in MongoDB. And that just strikes me as this is the 2020 world of access. It's convenient, it's got some nice things about it, but there's going to be an industry out there for decades of taking all the things that they build in MongoDB and putting it on a real SQL database. So, I have for you 2 articles to read, 2 web pages on why you should never use MongoDB. But basically, this upcoming week or so, we're going to look at how you install and how you use MongoDB and become familiar with MongoDB. That's where we're going with this. I wanted to pick out some things out of some of the papers and actually read them to you in case you haven't gotten to them. There's Google's F1 paper from the conclusion. In recent years, conventional wisdom in the engineering community has been that if you need a highly scalable, high-throughput data store, the only viable option is to use a NoSQL value store and to work around the lack of ACID transactional guarantees and the lack of conveniences like secondary indexes, SQL, and so on. When we sought a replacement for Google's MySQL data store for the AdWords product, the option was simply not available. The complexity in dealing with ACID data stores in every part of business logic would be too great, and there was simply no way our business could function without SQL queries. So having this this ability to actually build tables and query stuff is kind of important. Instead of going NoSQL, we built F1, a distributed relational database system that combines availability, throughput, and scalability of NoSQL systems, and the functionality and usability and consistency of traditional databases, including ACID transactions and SQL queries. So, you know, there is a way to do this, okay? And they're not the only one. There is CockroachDB out there that has done the same thing. Now, F1 is the SQL database on top of their reliable data store, and it is eventually morphed into what you can use in Google Compute Engine as Spanner. But the Spanner paper, okay, also gives us a clue that this is going on from the Spanner paper. A prime motivation for this evolution towards a more database-like system was driven by experiences of Google developers trying to build on previous key-value storage systems. The prototypical example of such a key-value system is Bigtable, which continues to see massive usage for a variety of applications. However, developers of many OLTP applications found it difficult to build these applications without strong schema systems, cross-row transactions, consistent replication, and a powerful query language. The initial response to these difficulties was to build transaction processing systems on top of Bigtable. That's out here in your applications. An example is Megastore. While these systems provided some of the benefits of database systems, they lacked many traditional database features that application developers often rely on. A key example is a robust query language, meaning that developers had to write complex code to process and aggregate the data in their applications. So, what Google found is that, yeah, they got rid of some problems when they used something like MongoDB, and they were a big MongoDB user at some point in the past. But they just moved those problems out here to the layer of the applications. They didn't solve them. So eventually they went back and they built this amazing stuff that actually solved these problems. So that's where they have gone. Now, I do have in the reading something for you to read about what is ACID, what is BASIC, how does it mean, what does it mean. We can dig out the original papers on this, but the little short web page that's maybe a page and a half long for you to read on what that is, it gives you a clear enough understanding. And I want to give you some idea of timing. All right, timing. Let's talk about performance. One of the grand claims of NoSQL databases is that they provided performance that you couldn't get in a SQL database. Now, this data comes from the last time I caught the other class, which is 5820, and I no longer have these systems, so I'm pulling out data from a year ago. The computers on which they were built are gone, decommissioned, gotten rid of. Man, they burned up a lot of electricity. I had these things in my household. One winter, they burned up enough electricity we didn't have to run the furnace. That was an expensive winter. But I built some tables here. Basically, I took the set of US patents, the text for all of them that was available, and 78 million patents, and basically took that text, 58 gigabytes of data, and I loaded it into two different systems, and then I did some tests on those systems. One was MongoDB, and the other was Postgres. So that's the basic test, and I looked at inserting 50,000 documents into each one of them, new documents, which would be about 2 months worth of new patents, and how long it took to do this. And then querying for specific terms in the patent. So there's an insert, and there's a query, where it searches for terms. Now, since these are documents, you don't have any good way to say this column has this kind of information in it. So these really are document searches, like what Google does. But out of that set of things, the 50,000 insert, okay, with just a single database running this took over here on Postgres 28 seconds. In Mongo it took 61. And when I did this with a set of 5 replicated machines, so instead of the original machines, I did this on a replicated database across 5 machines, we see that this turns to 32 and 41. So in both cases, the insert got a little better as we added hardware, but not a lot. But you will notice that in both cases, Postgres is actually outperforming MongoDB. And this was done with 100 clients talking to it at once. So certainly for inserts, okay, Postgres is the winner there. Now for queries, Postgres has a GIN index that allows us to effectively search these things. For a single machine, it took basically 11 seconds over here and 38 for a search for terms. This search for terms here required some special processing in the application to build that search. The search was much simpler with the query language and the GIN indexes in Postgres. So again, it looks like Postgres is the winner. And if we look at doing the same thing with the replicated systems, what we see is that with the replicated systems, this drops to basically 9 seconds, and that this is 35. Now, the fact that these numbers improve over here tends to indicate that MongoDB has some level of linear scalability that actually improves things as it adds machines. But we're also seeing some of that over here. Now, I don't know that these values are statistically significantly different, but what we're seeing is that in both cases, Postgres, with its GIN indexes and its 30 years of experience in tuning and making the database fast, is actually outperforming at scale MongoDB. So if you build an emulator for MongoDB on top of Postgres, I'm hoping we can actually be faster than the original. And you get queries as a nice added-on benefit. So that's what I'm hoping for. Now, I don't know if that's the case. Sometimes you go and build things, and the only way you can find out if what you suspect to be the case is true is actually go and build it and try it and use it and time it. Now, to use it and time it, we're going to have some software, and that's where we start, is in the wire protocol with the software to do the timing for how this is going to work. But these kind of numbers give me at least some hope over here, okay, that when we get done, we will say, hey, not only do we have a Mongo killer, we've got a Mongo killer that for most applications out there is faster and has backups and has reliability and works on all sorts of platforms and has a scalability solution on the back end of it, CockroachDB, that can take it to 10,000 times this performance.